Okay, my opening gambit is this. This is my favorite, all-time favorite rock guitarist. I could have gone with Hendrix, but I thought, a bit cliche-ridden. This is my favorite rock guitarist. Anybody who can tell me who that is, or even which band he's in, will get a signed copy of this. You're not even close, guys. Just come and tell me, okay? Signed copy of this. Probably worth $30 at least. If I sign it, maybe 25. Peter Frampton, get out of town. I'll give you a clue. He is not from this country. Moving on then. Okay. Research trends this millennium. This is basically what we're up against, or what I'm personally up against in academia, or the university profession, if you prefer. Because the fact is that within my research area, which is membrane bioreactors and membrane technology generally, there is a very, very large preponderance of research into membrane surface fouling. People go mental for this stuff. They analyze the individual foulants, which is generally extracellular polymeric substances, which somebody mentioned yesterday. This is EPS, extracellular polymeric substances. I just prefer to call it what it is, which is bug shit. And that is the stuff which is excreted from the surface of membranes, from microorganisms. Microorganisms, if you shock them with something like salinity, they excrete more of this stuff. So in that sense, they're not much different from us. If you get scared, nasty things happen. So microorganisms do the same kind of thing, right? So there's an awful lot of research into EPS. Then you've got things like nitrification, denitrification, which although might have seemed a little confusing when it was explained to you yesterday, it's kind of considered to be almost academically a done deal. So the research in that area is actually going down. But if you look at other things, phosphate removals remain pretty much steady. Obviously, phosphate's a very, very big thing in terms of a pollutant. It causes eutrophication, as you all know. So research in that has been pretty steady over the last millennium or so. Since the start of the millennium, I should say. Anaerobic MBRs steadily increasing. Again, academics go nuts for anaerobic processes generally because, of course, potentially they are energy-free, potentially. But there's a few challenges to get that working on something like municipal. But if you look at sort of really important things like cost and energy, well, energy, there's a little bit of energy research because it is associated with anaerobic processes. Cost, academics don't care about how much stuff costs, really. There's a little bit of research into cost. There's cost analysis, which is mainly, it's my area, which I tend to look at most of all. Because you've got to think of the most important things in life, which of course is money. So that's what I research. But not so much as other areas, according to my other academic colleagues. Of course, the total number of research papers has gone up significantly, but that's the same with all research. All research is basically increased in volume because there's just more stuff being done year on year. What you don't find, on the other hand, is any papers at all, pretty much, in this rather key area, I think we've decided, of membrane channel clogging. In fact, the total number of papers, the total since the dawn of time, if you like, is less than 10. I know this because I am responsible for about 6 of those 8 papers. So there's not an awful lot of research into clogging. So in fact, what I'm going to tell you for the next 40 minutes or so, I apologize for the lateness. We're 10 minutes behind schedule, or in academic terms, about 20 minutes early. But I'll try and stick to my allotted time. In fact, I can tell you every single person that's researched this particular area of membrane channel clogging. So starting with Marcin Stefanski, we'll hear more of him later, but he was the first person to actually try and analyze ragging in full-scale plants. Sara Gabaron at the University of Girona, again, a sort of ragging and clogging investigator. Tamas Zirai at Cranfield did sort of pilot-scale clogging tests under controlled conditions. Zhao Zhao Wang was also at Cranfield as a visitor, as was Sara Gabaron. And he's now at Hebei, and again, looking at clogging. And then where I am at the moment at Cat University, we have a crack team of Gianna Jamaluddin, Pompilia Bazatu, and Albert Odai, all of whom are working together on MBR, clogging, and indeed ragging. And before I go any further, I think I ought to be quite specific about what I mean when I use the terms ragging, sludging, and clogging. These are all terms which are used in the industry, but they're not always used consistently. So permeability decline. Permeability you may refer to as specific flux. It's just the ratio of the flux per unit pressure. That is, according to 99.99% of all academics, is just attributable to membrane surface fouling, the coating of the membrane surface with these extracellular polymeric substances which then reduce the flow of water through the membrane. However, what we're rather more familiar with as practitioners is the phenomenon of clogging. And clogging is just the coming together of solids in whatever place is the most awkward for the smooth running of the process. Fouling is normally defined as either reversible or irreversible. If it's reversible, then it's removed physically by a backflush or a relaxation. And if it's irreversible, it's not actually irreversible, but it's only removed by chemicals. So essentially, if you have a combination of some kind of physical clean and some kind of chemical clean, then you can normally maintain the permeability if your only challenge to the process is membrane surface fouling. But you know, life is never that simple. And we do have clogging. And clogging is normally defined as either sludging, which is the filling of the membrane channels with solids, or, and that's just an example of a panel pulled out of a plant in Scotland. But it's not just limited to flat sheets. You can get clogging of hollow fibers as well. Or you have ragging, or it's sometimes called braiding, but I prefer the term ragging. And ragging is basically the blocking of the membrane channel inlets by the formation of these rags. And Jim, yes, I have stolen this picture from you. Sorry. And I didn't even ask permission, but look at the length of those rags. Fantastic. The amazing thing is, those rags are actually formed of little filaments which might be no more than like half an inch long. And yet you're forming something which is more than a meter. Amazing stuff, more of which later. Okay, so why bother studying this? Clearly, pretty much all of my colleagues don't bother. But the reality is that membrane permeability is maintained through air scouring and backflushing, which are physical mechanisms to remove solids, and chemical cleaning to remove organics. That is how a membrane process is sustained in terms of its permeability or specific flux. But the efficiency of these things is basically limited to the membrane surface. So you backflush to remove the solids from the surface. You chemically clean to remove the colloidal species and the dissolved organics from the surface. That's what they're designed to do. But once the membrane clogs, i.e. the gaps between the membranes, and there are, what is about 6 millimeter gap between one membrane and the next in a flat sheet module. Once that becomes filled with solids, what happens at the surface becomes completely irrelevant, because the water can't even get to the surface of the membrane. So it doesn't matter whether you've characterized the extracellular polymeric substances into carbonate and protein, and whether you have bipolymers and what sort of species you have and what their molecular weight is and how they charge, react, and all those other things and solvation forces. It doesn't matter, because the water's not even getting there. And to make sure it gets there, we have to address the issue of clogging. So, how do you study clogging? Well, the short answer, friends, is with great difficulty. And that gives me a little clue as to why I'm the only person that actually bothers studying it. Because I'm pretty stupid, and I like to make life really hard for myself as often as possible. It is quite hard. There isn't a standardized, accepted methodology for quantifying clogging. Naturally, most academics don't even realize it exists, so having a standardized method is some way off. But we do have little things that we can do to try and quantify it. Certainly, as far as the published research in this area is concerned, and remember, there's only 10 papers, so it's quite easy for me to summarize them, particularly as I'm the co-author of nearly all of them. But the efforts thus far have comprised gravimetric analysis, which is just weighing it, basically. That's what that means, of solids which have been extracted from the membrane. And that was done by Buzzatu et al. She is now at Kata University. There's gravimetric analysis of clogged solids within the membrane module. So basically, you just weigh the membrane module before and after it's clogged. That was done by Zira et al., again at Cranfield. And then we've got a number of qualitative studies for ragging, and that includes Stefanski et al. And indeed Gabaron et al. So these are sort of some pretty key papers in this area. And as you can see, there just aren't that many of them. So looking at the work at Cranfield University, these were all done at pilot scale. They're all done on hollow fibers. Basically, it's just because those are the guys that gave us the money. They were only interested in hollow fibers, so that's what we investigated. But the same principle will apply to flat sheets in terms of the methodology. In situ determination. Basically, this is the easy way. This is the Tamas Zirai way. He doesn't want to make life too hard for himself. He just used one of these, a very sensitive load cell. So you're given that the module itself weighs, I don't know, maybe quarter of a ton or something like that, then you need a fairly sensitive load cell in order to weigh the difference between the wet module and the wet module with the clogged solids. So it's a bit rough and ready, but it's a damn sight easier than the ex situ method, which involves extracting the solids from the module, which is very, very accurate, but for that you do need this, i.e. 2 visiting students at Cranfield University. So they arrive sometime in June, and they say, what am I doing? Well, the good news is you'll be working in MBRs. Yay! For Simon Judd, yeah! And you'll be extracting shit from modules for 3 months manually. Yeah, I still get their hate mail. So that's the way of basically analyzing clogged solids. That's how you do it. Of course, if you're analyzing rags, then you need some very, very high-tech equipment, very high-tech. Basically, you need one of these. And this is what Marcin Stefanski did in, well, it must be getting on for 9 or 10 years ago now, when he just basically traipsed around Wales and the west part of England, where we have a lot of flat-sheet MBRs, some very old flat-sheet MBRs, and basically just fished for rags using a regular fishing net. And he then was able to sample quite large volumes. If you do the math and work out the area of this, you've only got to drag it about 10 or 12 meters and you've sieved a ton of sludge. So it's a pretty simple and effective thing to do to collect these large solids. You're only limited by the aperture of the net, and in his case it was about 4 millimeters. So he called this test the CSS 4000. Sounds good, doesn't it? It sounds like an advanced photocopier, but it's actually just a method for sieving coarse solids. And that's what you end up with. It looks pretty unappetizing. I don't think you'd want to eat all of that at once, unless you dine in Greggs in the UK. So what he did was basically defragment it, pull it apart, and then rolled it back together again, and found that he formed basically a mechanically stable rag. Then he thought, well, let's play with it a bit more. He washed it again, reformed it, still formed a rag, washed it in soap to get rid of all the surfactants, still reformed the rag after washing. So effectively, he figured that this stuff was pretty mechanically strong, so he thought, right, let's hit it with hypo. If you hit something with hypo, you dissolve all the hair. So people, if you ever want to dye your hair, don't use bleach. Just a bit of advice there, because bleach does actually dissolve hair if you leave it overnight. If you do that, you end up with a nice white material. Wash that again, still forms a rag. So basically, the idea that rags might be formed somehow from human hair is not true. It does seem to be some sort of textile material, and everything points to cotton wool as being the beast responsible. So, taking that theme a little bit further, at Kata University, we've just been looking specifically at rag formation, and just using a completely made-up method, which seemed reasonable to us. So, what this involved is it's basically a gravimetric measurement. You add a cotton wool standard, and indeed we've managed to get hold of some real rag samples from a UK MBR in the Wessex region of the UK. We've also taken some lint from laundering, so you basically just take the filter out from your tumble dryer. I took a handful of that and shipped it off to for doing this test. The sample preparation, basically, you have to cut the material into lengths of less than 5 millimeters, because you have to figure that anything that arrives in the membrane tank has gone through a 3 millimeter screen. So you can't really have lengths more than 5 millimeters. That's kind of the premise that we've used. Cutting up cotton wool into 5 millimeter lengths and then trying to isolate each individual fiber is impossible. Well, it's not impossible, it just takes a long time. So guess what you use to do that? Yeah, students. So that's what they've been doing. They cut up the fibers into 5 millimeter lengths, and you just tease them apart and tease them apart so you have the smallest possible aggregate of fiber, something which just sort of you can pick up with the point of a tweezer. It's that kind of size, less than a millimeter in a bundle. But to do that, you have to do that in order to make sure that when you add the fibers to the water for the test, they are basically completely dispersed. So the test we use is to add just 100 milligrams to about 15 to 20 liters of water, which is only about 6 or 7 milligrams per liter. And if you think about it, 6 or 7 milligrams per liter, you maybe have 10 grams per liter in your MBR sludge tank. So we're talking about 0.1% of the total solids being as fibrous material. It's pretty damned low. So this is the way it works. You stick them, add them very, very slowly to the tank. It's very gently stirred, and you try and ensure that all these things initially are completely dispersed. Leave that running overnight, and something magical happens. You do actually form an aggregate, a single aggregate. So pretty much depends, but somewhere between 15 and 80% of the fibers that you add will form just one rag. And you can then, just to test its mechanical stability, you can actually remove it with a pair of tweezers if you do it very delicately. So I think that's Pompilia's hand removing these fibers. She's very, very protective of her rags. She likes to try and remove as much as possible without it falling apart. Very, very protective. It's probably the closest she'll ever come to having children, is to have these rags that she gently pulls out. So essentially, you can form these aggregates from this completely dispersed bunch of fibers that you're adding to the tank, which I just find fascinating. You can add something completely dispersed and it just forms one aggregate. If a coagulant could do that, any other process would be dead in the water. But these fibers do actually aggregate to form like more or less a single rag. And that's what this summary table shows. And there is quite a large difference in behavior. So the lint, for example, on the bottom line here, doesn't form rags at all. You think, well, lint is just cotton, you know. Most of the clothes I have at home are cotton. I just pulled this lint from my tumble dryer. Cotton wool is cotton, but the cotton wool forms a 53% rags. The second time we did it, it formed rather less rags, behaves rather differently. Same stuff, same cotton wool, slightly different behavior. The sample that we pulled from the Wessex Water MBR ragged like crazy. So clearly, there's something happening which causes rag formation. The rag formation is really quite significant. We've got very low concentrations, yet it forms just a single rag. If you extrapolate that to a full-scale MBR, where you have several tons of sludge, then fairly obviously you can form much bigger rags because they stay in the membrane tank for quite some time, or they stay in the whole system for maybe 20 days if you've got a 20-day SRT. So clearly this is a real effect. We don't really pretend to understand why it happens, but it's certainly happening, and it can be quantified using this very simple method. Okay, that's enough of ragging for the moment. We're going to move on to clogging now. This is a little bit more involved. This is the test that we've used for that. Essentially, it is just a single A4 size membrane panel which has a viewing window into it. So you can actually see what's going on in that panel. And all we're trying to do is clog the channel. There's a 6 millimeter gap between the perspex wall and the membrane. So, first of all, a little bit of background into the science of fouling. Fouling is normally measured by the dP by dt pressure gradient, the rate at which the pressure increases at a constant flux, something which I'm sure you're familiar with if you're on your plants. And that follows the relationship of pressure incline rate equals some value multiplied by the exponential of the flux multiplied by a second value. It's a classic exponential relationship. And what it means is that when you plot the pressure incline rate against the flux at various flux values, you get a straight line if you have a logarithmic scale on the y-axis and a regular scale on the x-axis. We used two different types of sludges because we had access to two different types. One was industrial, one was municipal. And you can see, and this is obviously intuitive, the industrial has a higher fouling propensity, a higher value of this fouling exponent than the municipal. Absolutely to be expected. And we did these correlations basically because you need to benchmark against something, you have to sort of make other academics feel comfortable, and this is the kind of stuff that they're used to. But it does give a measurement of the rate at which the pressure is increasing or the rate at which the permeability or specific flux is declining. So it's a good benchmark to have. As far as clogging is concerned, well, this is completely new. You are, in fact, the first people to be told this apart from our collaborators. What we've done is operate at a constant flux, so we're operating that cell I showed you earlier under constant flux conditions, operate it for an hour or something like that, drain the membrane channel to reveal the clogged solids, and then photograph it. You then reload the reactor with the sludge and just carry on. Stop for another hour, stop the next hour, take a photograph, carry on. So it's just a repeated thing until you've sort of got to about 4 hours and it's time to go home. And for each time you take the photograph, that image has to be processed in order to quantify how much of that channel is filled with solids. It's probably easier just to sort of demonstrate it. So you stop after an hour, you end up with this kind of pattern. When you digitize it, it's then much easier to differentiate between the unclogged areas, the white area here, and the clogged areas, the brown area. So apparently about 10% of that A4 panel has been coated with these brown solids. It goes up quite quickly in the second hour to 77.8% and then to 89.3% in the third hour. And you can work out the clogging rate from that just by dividing by time. So you get a rough indication. If you always run to the same time, 4 or 5 hours, then you can get a rough indication of how fast the membrane is clogged. So you've basically got two key parameters. The clogging rate, how fast the membrane is being clogged, and the fouling rate, the rate at which the pressure increases with time with flux. So one is kind of a measure of fouling, provided you haven't got any clogging, and the other is a direct measure of clogging. So those are the two key parameters we're looking at. In the actual tests, we did 3 campaigns altogether, used industrial sludge and air scoured it under normal operating conditions. The industrial sludge, as you will see, is the most challenging in terms of its operation. We had industrial and municipal sludge with no air scouring, so effectively we're really encouraging the system to clog because that's what we're trying to find out about. You still have a little bit of what's called shear in the system to allow the water to pass through the membrane, but if you haven't got any air, that shear is much lower. Shear is basically this. If I've got a flat surface here and I've got water or a fluid flowing across it, by doing that, I'm generating shear at the surface. It sort of manifests itself in a slight change in the temperature when you do it with your 2 hands. But that's all it is. That's what shear is. So those are sort of accelerated clogging tests. And then we thickened the sludge up and did the same thing both with and without air. So essentially, we are encouraging clogging by doing this. So a lot of these results that you see might look quite horrific, but they are basically, we are forcing the system to clog so that we can study it. So here are the outcomes. First of all, the key measurement that we did was the rheology measurement. Rheology is basically how viscous or gloopy something is. And water, for something like water, the measurement of that, the viscosity, doesn't change with anything other than temperature. So it doesn't matter whether I'm shearing it at this rate or at this rate. The viscosity stays the same. Thing about sludge is it's not like that. The viscosity changes with shear. This is a very, very well-known thing. Again, some of my academic colleagues who study sludge rheology, they go mad for this, how the viscosity changes with shear. And it is actually quite important. If you're trying to pump sludge, then you really have to know that kind of stuff. Because if you get to a point where you can know where the viscosity becomes very high, your pump's not going to work. So actually, sludge rheology is something that's worth investigating. And what we did with this extraordinarily expensive rheometer that we just happened to have in the department was measure the viscosity with shear. Doesn't really matter why this is, but the net result is if you just pick a whole bunch of samples, you get this kind of behavior for the municipal sludge and this kind of behavior for the industrial sludge. So if you get up to this point here, that's about 120 per second shear rate, which is kind of representative of what you might find in a regular MBR. Those are the sort of shear forces that you'd expect. Then you can see there's a massive difference in the viscosity of the industrial sludge and the municipal sludge. So this is just a characterization thing. And I'll come back to the significance of this a little bit later. Then there's the fouling stuff. Now remember, the fouling propensity or the fouling exponent is just that number in the equation which represents how rapidly something fouls with flux. So it's just a number to give you an indication of how bad the fouling is going to be. And again, you get two different sets of behaviors for the two different types of sludges. In essence, the industrial sludge is more highly fouling than municipal. The key thing is you take the gradient of this line and you've got a number which then quantifies the relative fouling propensity of the two sludges. So we've got one sludge which is pretty benign, the municipal sludge, and we got one sludge which is pretty difficult. And we're just trying to compare the behavior of the two. Okay, CST. Hands up if you know what CST stands for. Anyone at all? Oh yeah, well, creepy head in the front row here. CST is a real cool measurement. It stands for capillary suction time. You can just buy a little machine, a couple of $1,000s, I suppose. I'm not sure how much it would cost here. And it gives you some indication of the dewaterability of the sludge really quickly. And you can, it's a very portable thing. It's not huge. So what we did was plot some of these things, the fouling exponent, against key quantities, namely the CST. An awful lot of sludge characterization is based on CST and SVI. CST is kind of more useful, so we went with that one. And as we would have expected, without going into too much detail, the longer the CST, so the more time you need to dewater something under these sort of specific test conditions, the higher the fouling rate. Absolutely typical. Same sort of thing, not quite as good a relationship with the COD, the soluble COD. We normally reckon that all of these things which foul the membrane, the EPS and the carbonate fraction of the EPS and the SMP, that's the soluble microbial product, and all these other things, they're basically organics. So if you've got more soluble organics, you've got more fouling. And again, this is kind of indicated. I forgot to mention we've got two different flows of air here. So when you apply air, you have a lower fouling rate than when you don't apply air. Again, it's one of those no shit Sherlock things. It's fairly obvious if you apply air, you're going to get less fouling. But we did it with and without air. And again, the industrial ones, more highly fouling than the municipal ones, and it could possibly be associated with COD. Okay, so we've done the scientific thing, we've plotted this against that, and it's pretty much as you would expect. However, and this is one important caveat, if you look at the way in which the different membranes, the different sludges foul or clog the membrane, there is a distinct difference. So this is the municipal membrane. So this is the membrane which has been challenged with municipal sludge, and the sludge is coating the membrane. But basically that is just a cake. It's not actually filling the channel. It's just a thick layer of foulant, if you like, enough to cause you a few problems. But chances are, if you applied chemicals, that would be removed. The industrial sludge, on the other hand, looks like this. And this is proper, oh my God, clogging or sludging, the filling of the membrane channels with solids. So under our experimental conditions, which I must stress, we were trying to clog the membranes, we were really pushing the system to its limit, we found that the industrial sludge was demonstrating clogging behavior. The municipal one, well, it was basically just very good quality sludge from an MBR called Luzeo in Qatar, which meant that we got caking, but not actually clogging. So in order to do a straightforward comparison under fair conditions, we looked at trends at a fixed flux of 20 LMH, and we found that pretty much everything increases going from the municipal sludge to the industrial sludge. The viscosity, how gloopy the sludge is, that goes up. The capillary suction time, how dewaterable the sludge is, that also goes up. The soluble COD goes up. The clogging rate, which we're calling percentage C, the percentage rate at which it clogs, goes up. And lastly, so does the rate of permeability decline, or specific flux decline, if you like. So basically, all that graph tells you, I mean, it looks very nice, you know, I like the color scheme, I like it, you know, those are my colors, I like to think. But all it tells you is that industrial sludge is more tricky than municipal sludge. Well, there's not many people out here that wouldn't be able to tell me that without me actually showing you a graph. So that doesn't really take us that much further as to why things sludge, and critically, does it relate to fouling? Because if all these academics are spending a lot of their lives, or forcing their research students to spend their lives to study something which really doesn't relate to one of the main impediments to MBR operation or implementation, they are wasting their time. So let's try and dig a little bit deeper. Okay, well, first of all, if you look at the clogging rate data and plot that against CST and do the same thing with COD, there is absolutely no correlation. So for the fouling rate data, that's the rate at which the pressure increases with flux, there is a correlation, roughly. For clogging, it's all over the shop, completely random. So you can't really say that clogging relates to fouling, not from those plots. So what does it relate to? Well, to do that, we had to just take one more variable and change the solids concentration itself. Because you've got to think, if you increase the solids concentration, there's a whole bunch of things that are going to change as far as the mechanics of the systems are concerned, like the viscosity has got to change. But the chemicals, the soluble chemicals should remain the same, because all you're doing is increasing the solids concentration. If the soluble chemicals are at the same concentration, fouling shouldn't be affected. So if there's a change, it must relate to the physics of the system and not the chemistry. That's basically the way we were thinking with this. So this is the money shot, really, of the whole thing. What happens when you change the MLSS from this region here, 8 to 12 grams per liter, and go way up to 15 to 22 grams per liter? There's not a lot of control in some of these numbers, but those were the ranges we were looking at. And we're looking again at viscosity, the capillary suction time, the soluble COD, which remember we're saying represents fouling, this surface fouling, which all my colleagues are obsessed with, the clogging rate, at U equals 0, that's with 0 aeration, and then the clogging rate when we actually aerate, and then this fouling exponent value here. What happens to all of those when you go from 8 to 12 grams per liter to 15 to 22 for both the industrial and the municipal samples? What actually happens? God, I can cut the tension with a knife in the room right now. You're there with bated breath thinking, tell me, Simon, tell me now. Okay, I'll show you. So basically, the viscosity goes up. No surprises. No surprises at all. If you have higher solids concentration, the viscosity's got to go up with this sludges. That's absolutely well known. It goes up for both the industrial and the municipal. The CST goes up, but only very, very slightly for the municipal. It goes up a lot more for the industrial than it does for the municipal. Why that is, I don't know, to be honest, but it doesn't go up that much for the municipal. The soluble COD, now remember, this is the stuff which we're saying represents fouling, roughly, actually goes down with the industrial. It's probably because of the way we thickened up the sludge, but it goes down. For the municipal, it goes up. Again, why? I have no idea, but that's just what happened in our test. Now, the key thing then is the clogging rate. The clogging rate goes up massively for the industrial sludge when you have no aeration. So basically, as soon as you switch it on, it almost locks up within an hour. So you get almost instant permanent clogging with the industrial one. For the municipal, it actually goes down slightly. But remember, the municipal isn't really clogging. It's forming this weird surface cake thing, which probably your CIP would get rid of in all reality. Whereas the industrial, no way would a CIP touch this. It's actually filling the complete channels. If you apply aeration, and this is of more practical significance, and I will show you why in a second. If you apply aeration at a fair old rate, you still get clogging for this industrial sludge. So even when you're operating under regular conditions, same conditions you would operate a regular MBR at, the same kind of aeration rate, maybe even a little bit more, at this concentration, you will get clogging. And again, more information on that a little bit later. As far as the fouling is concerned, fouling again, this is the pressure incline thing that I told you about before. So the pressure incline rate's hardly affected by clogging, which is odd. But the municipal, which isn't really clogging properly at all, you do get a change in fouling. So basically, fouling doesn't equal clogging. It means when you're sitting there scouring the outputs from your, I forgot what it's called now, SCADA, and you're looking at the pressure data, you can't actually tell whether any change in pressure is associated with clogging or fouling. The only way you can tell whether you've got clogging, really, is to, one, see whether you get a recovery after your CIP. If you don't get a recovery after your CIP, you might have some really strange fouling going on, like the guys yesterday that had that sort of inorganic fouling, which is still quite rare, I think, to get inorganic fouling in a regular municipal MBR. Or chances are it's clogged. So as I said, CIPs are designed to remove surface fouling, and they're very effective. But if you get clogging, I'm afraid your CIP just ain't gonna do that much. So basically, clogging doesn't relate to soluble COD, so it doesn't really relate to fouling. So this fouling exponent, which we use to quantify fouling, doesn't relate to the clogging rate. There is some indication of impact of clogging by the CST or the rheology, but it's obviously a very complicated thing. Just because you have high viscosity or high solids doesn't necessarily mean you're going to get clogging. So why does it happen? Well, at this point, I can show you my dirty video. This is my dirty video. This is basically just shooting a video of that Perspex channel face on and watching the bubbles climb up through the sludge at, ooh, blimey, sorry, something wrong there, at 3 different concentrations. Actually, I'll use this. If I just run this right here. So we're going at 15 grams per liter on the left, right the way up to 23 grams per liter on the right, and we're just aerating the channel as you would do in a regular MBR. And you can see, first of all, the bubbles are bigger at the higher concentration than they are at the lower concentration. Also, if you squint, you can probably see that the bubbles for the low concentration are more or less scouring the whole width of the channel. Whereas at the 2 higher concentrations, they tend to sort of disappear up to just one part of the outlet. It's probably easier to see when you run at regular speed like this. You can see they're sort of like disappearing up to one side, or through the, more or less through the center of the channel. And that's manifested in taking a look at the channel at the end of the experiment, where you can see that clogging tends to happen at the sides, and also this center bit between 2 holes of the aerators. So it's pretty much as you would expect. You're getting clogging in line with the aeration pattern. What then causes the aeration pattern? Well, it is actually known that if you have high viscosity fluids, the air bubble stream tends to constrict. This has been known for about 10 years. There's a company called Praxair who looked at this. The researcher was a guy called Malcolm Fabie, and he showed his results at WEFTEC in 2008. So it is known that if you have very, very high, highly viscous fluids, it will affect the aeration. What causes high MLSS? Well, it's some fairly obvious things. If you don't waste, your solids concentration will go up. If you decrease the recirculation rate between the membrane tank and the process tank, again, the MLSS will go up. If you increase the flux, same thing. If you increase the organic load, you'll grow more MLSS, and as a result of that, the solids concentration goes up. So you could say a simple message is control the MLSS and control clogging. It's not quite that simple though, because the fact is the nature of the sludge, the fact that industrial sludge is just a different animal to municipal sludge in our experiments, that will also affect clogging. So basically we've gone a little bit further with understanding clogging, but it's really a long way to go. It's very, very lonely studying MBR clogging, and we could do with a few more researchers looking into it. So the ragging stuff, well, we need to actually analyze rag's composition to see whether it really is just cotton wool, which is the main offender when it comes to ragging. Clogging, there's all kinds of stuff we need to do to try and understand further clogging. One of the things is to actually completely control the shear rate by doing it mechanically, and we're able to do that with our test. But most of all, more site-based data, because essentially we can't really hope to understand something as complex as ragging and clogging unless we have more information from individual sites to try and pull out the rags, try and understand the nature of the way in which the sludge flows, and then use that as the basis to further knowledge. And of course, for that, guys, it's over to you. And that, my friends, is that. Thank you for listening. Well, I feel a bit strange sort of asking myself to ask for questions, but if anyone has any queries, that's fine. If not, we can go straight on to the next talk. Yes, sir.
In terms of the industrial sludges that you tested, can you be a little bit more specific about what type?
Yes, I certainly can. It was from a combination of produced and processed water from a gas processing plant. I can't tell you too much more than that, but basically it's like produced water from a gas field which has been diluted to some extent from processed water from the gas processing operations. Pretty nasty, actually.
Can you give me a rough idea of what the components of it were?
Actually, no, not really. It's going to contain a bit of dissolved oil, obviously. There are all sorts of organic process chemicals used in that plant. I think if they told us exactly what they are, they would have to kill us. And that's okay for me, I'm an old man, but some of my researchers, So we don't really know exactly what they are, but you can reckon on them being organic chemicals combined with organic process chemicals used in regular gas processing, combined with the dissolved fraction of a gas field wastewater. I can't tell you more than that. It's a good question, though. Yes, sir.
So the ragging charts which you showed was that industrial is always the high rate for ragging. So is this accurate for all type of industries, or it depends on the type of industrial wastewater? Like, let's say take food and beverage industry. So can we say that it's similar to the
Well, you won't get ragging in a food wastewater, will you? Because there's no cotton wool or textiles in a food effluent wastewater. Ragging, I think, is specific to municipal and maybe textile effluent. I tried to get more information on textile effluents via LinkedIn, but didn't really succeed. Clogging, good question. Obviously, I guess this relates to your question. This is a very tough wastewater, which they're treating using an MBR in that particular industrial site in Qatar. And they do run at a very low flux to try and mitigate against clogging to a large extent. But I think it's probably one of the toughest. If you go for food and beverage, I don't think it would be as tough as the industrial sludge that we use. We kind of hit the jackpot in terms of being able to do our study on on a sludge with such a high clogging propensity. Yes, sir.
Did the plate distance matter in the clogging?
That's a good question. We don't actually know. There's so many variables you could look at. It must mitigate against it to some extent, but of course, if you increase the plate gap, you're increasing the energy demand, and which is why pretty well all of the suppliers go for a gap somewhere between, say, 5 and 9 millimeters. You won't find anything above 9 millimeters, and possibly these days no more than about 7.5 millimeters. And it's just down to money, because if you are rating a channel which is this big instead of this big, you're basically, the amount of air you need volumetrically is in direct proportion to the gap. So yeah, it probably would make a difference, but I don't think anybody's going to rush to produce wide-gapped MBR channels. Doesn't seem to make sense. Yes, sir.
Yes, the ragging issue, did you consider the wood fiber that comes from the paper making process for making toilet paper?
Yeah, we've actually done that test already. So are you thinking of that maybe bathroom tissue being, it's not bathroom tissue. No, we did that very early on, actually at Cranfield, like 5 years ago. I think Stefanski looked at that and looked at different materials. That's how we know that hair is not the issue, bathroom tissue isn't the issue. It really is cotton wool or some kind of textile. If there are other textiles in there, like rayon might be another one. I mean, what actually causes ragging, what causes these things to come together? It could be the nature of the surface. There are irrigosities in cotton, which there aren't in nylon, for example. It could be solvation forces. It could be hydrogen bonding. My personal explanation, I think, is that these fibers are enticed by the devil, and that's why they come together. Yeah.
Is the amount of fiber in the waste related to the amount of laundry?
Is the amount of fiber related to the laundry? That's another good question. It's odd, isn't it? Because the lint, which is basically where you would think, it's just the sort of, it's just the stuff from the laundry, isn't it? If you collect the lint from your tumble dryer, then it's stuff which hasn't ended up being ejected in your liquid stream. The lint did not rag at all. So it's a complete darn mystery to me as to why some fibers rag and some don't. It's a bit more obvious why bathroom tissue doesn't rag, because it is a different thing. It's a wood-based thing, whereas cotton plainly isn't wood, and neither is wool. But we haven't got as far as looking at the composition of the rags. We've only just used cotton wool as a standard, and we've done just one sample from Wessex Water. Like I say, we could really do with more information from sites to find out more information about the nature of the rags in reality. Because all we've got is like literally a washing up bowl with water and a little stirrer. It's exactly as you saw. We want more information from site on the composition of the rags from real rags. That's what we would like. Yeah, okay.
Did your stirring study, did it form one and then build on that, or did it form multiples and then allow?
That's a good question. The fact is, sir, Could be either of those two. We were asleep because we left it overnight. It's just, it's just magic. It's like, here's one I made earlier. You come back in the morning and, oh, we got a rag, And sometimes it rags. Sometimes it formed little agglomerates on the bottom of the tank. Sometimes it just formed 1 or 2 rags. But we don't actually know how that happens. Perhaps I should force the students to stay up all night watching it. Or maybe I should just buy a video camera. But I prefer the first option, so I'll do that. Yeah.
A couple of years when he brought this up, that this is something new in industry, is it the baby wipes and the flushable wipes? Because you actually made me go home and look at the composition of it,
Oh, really?
and it really does have cotton on there.
Yeah, I think there's all kinds of stuff. I'll tell you something which is quite interesting. As far as I'm aware, maybe in the whole of in the Middle East, but certainly in Qatar, in the municipal plant in Qatar, it's quite a big one, Lusail. They don't see rags. It's clearly a cultural thing, and I don't know. Perhaps we could have a show of hands. Okay, so guys, when your other half puts on her makeup or whatever and applies cotton wipes or anything like that, does she do this in the bedroom with a sort of like a dresser, or does she go in the bathroom and do it there? So hands up for the people whose wives use the bathroom when they put on their makeup. Okay, stick your hand up if you know for sure that when they do that, they stick the cotton wool down the toilet. You wouldn't know, I guess. But it's a 50-50 as to whether she would throw the cotton wool into a trash can or down the toilet. If it goes down the toilet, well, you know what happens in terms of the MBR. Whereas I know, I was discussing this with my colleagues in Qatar, and they were saying, well, we've got a dresser. She just uses the dresser, and then there's a trash can by that, and she just does that. So the dresser is in the bedroom. The idea of going into a toilet, put on makeup is apparently not the normal thing. So it's mainly a cultural thing. One last question, then we've got to move on. Yeah.
Municipally speaking, in your opinion from your research, is there a mixed liquor concentration where the rate of return is?
Yeah, actually there is. I would say we've had this discussion with Dennis, and Dennis has got, he's better informed from anecdotal site information than I am. But we found from the Zero et al. Study, it's around about 18 grams per litre. At 18 grams per litre, it does kind of go off a cliff very slightly. I mean, I would say recommend stay well below 15 and preferably below 12 if you possibly can. But again, I should stress, rheology is a really, really weird thing. And even when we went up to tremendously high solids concentrations for this Lusail sludge in Qatar, it just didn't clog because it was just really good quality sludge. But as a rule of thumb, I would say stay well below 15, and at 18, most likely you're going to have problems. I think we're going to leave it there, guys, because I've overrun. Yeah.
Clarify real quickly. You talked about thickeners running a
Oh, I beg your pardon. Yeah, I'll just mention that. So basically, what I said just now about rheology being really weird, the fact is when you go even higher, so you have like several percent, in fact, of solids in your mixed liquor, as would be the case in thickeners, the rheology changes again. And you can see that. Anybody that's got an MBR which has got a thickener right next to it, and there are a few sites like that, if you sort of, if you've got nothing else to do, if you actually stare at the air bubble pattern on the regular MBR, it'll look completely different to the air bubble pattern on the thickener. The thickener, it looks like a witch's brew thing. It's going bloop, bloop. It's really quite disgusting, actually. But it looks different because the rheology is different, and the way in which the air bubbles come up through the liquor is different. So you can't assume that you're going to get the same clogging behavior, even though you've got really, really high solids concentrations, because the rheology has changed again. It is a very, very complicated subject. Thanks for reminding me of that, though.